Is it better now?
Yes, a little bit.
Okay. Okay. So probably we'll have to go this way, just this way. Hello, hello everyone. Thank you very much, Utkatani, for the organization of the workshop, the invitation, and a nice introduction. So today, as you can see from the title, I'm going to talk about the causal representation learning and generative AI. And by causal representation learning, I mean learning the underlying causal structure, including hidden causal variables and relations. And in the first part, you see the recent advances in causal representation learning. And in the second part of this talk, you are going to see the implication of causality in generative AI. So you can see how we can learn the hidden things and make generative AI more accurate in some way. Okay. So let's start with the story right here. As in Europe, I think you are familiar with this story. So, until the mid-19th century, puerperal fever was very popular, right? Because of that, a lot of women didn't survive after giving birth. So, how could you find the reason? So basically, they found that in Vienna, there were two clinics with almost the same techniques, but very different mortality rates. And now comes the hero, Ignaz Semmelweis. Basically, he examined all possible factors by comparing the two clinics. And finally, he came up with the hypothesis that the puerperal fever was caused by some unknown, unseen, cadaverous material on human hands. Okay, and now you can see at that time he couldn't really see it. However, because of the comparison, he could come up with this hypothesis regarding the cause of the phenomenon or the disease. And then, just because of the hypothesis, he could just propose the intervention, which is very simple, right? Washing hands properly. And then the world became very different after that. So at that time, this hypothesis conflicted with the established scientific and medical options, medical opinions of the time. At that time, people believed that the disease was caused by the four humors in human body. However, later, this theory was accepted by the community because of Louis Pasteur and others. So now you can see, basically, whenever we could really discover the essential hidden entities or hidden laws, the world can become very different, right? And as you can see here, this is our world. So you can see what we can see is actually very limited, shaped by what we believe exists and how we understand it. From the observed data, we try to figure out the existence of hidden entities and their properties, and then try to come up with new ways to measure them or even manipulate them. This way, our world is becoming bigger and humans are becoming more resourceful. And however, this progress has been very slow. So to address this, our long-term goal is to develop an automated platform for scientific discovery. And this way, we can just take all the measured data as input and then produce plausible hypotheses regarding what should exist there, how to verify them, and so on. And this way, we can just keep increasing human world in a sustainable way. Okay, I'll skip this. So now let me just give some examples, motivating examples. Later we'll come back to these examples regarding how we can learn causality and how we can make use of causality to improve generative AI. So this is the first one. Right here, we have the data collected by our collaborator. So they measured 250 skeletons in the world and 8 variables of the 250 skeletons, and they try to see the causal relations among different features. So now you can see in this case, first of all, we cannot really do any intervention to see the consequence. We can only make use of the observed data and try to see the causal relations among those features, including geodistance, climate, diet, cranial shape differentiation, and so on. Okay, later you can see the result. Now comes the next problem. So each of us try to understand our personality, but how? We can never directly touch our personality, right? We even don't know how to really figure out where the personality should be. Instead, we can design questionnaires, and then from the answer scored, we try to infer the underlying mental conditions, right? So in this way, we can try to infer the underlying hidden causal variables and relations. Later, you can see how we can automatically determine the dimensions of personality by making use of the answer scores as a typical causal representation learning problem. Now let's look at generative AI. Specifically, let's look at the result of image generator. So we have been doing these experiments for 2 years. So the prompt is a peacock eating ice cream. So this is a very unusual scenario. However, we can produce some sensible picture, right, from this prompt, because we know what you mean by peacock, what you mean by ice cream and eating and so on. So basically, we know concepts. We know relations among concepts. Now comes the result by Stable Diffusion produced 1 year ago. You can see, yes, it's a very nice picture, but where's ice cream? And why? This is very simple, because in the training data, there is no such a picture, right? And it's very hard to generate something very plausible. And months ago, now you can see with DAR3, it's much better. However, if you have a closer look, you can see something similar. You can see something interesting. Right here, you can see in almost all cases, peacock is using human hands right here. And actually, it's not really eating, right? If the beaker just touches ice cream, it's not really eating. What's the problem? Now you can see they can try to put things together, but not in the right way. Later, you can see how we can solve this problem. Okay, now comes the first essential question. What's the difference between causality and dependence, right? We know causation implies correlation, but correlation doesn't imply causation. But this way, I don't think this statement is fair. Maybe it's better to say correlation doesn't directly imply causation. However, in almost all cases, by analyzing observational data, we can really see something about the causality. So basically, this caricature explains my experience. When I was very young, I used to think correlation implies causation, and then I still remember I read a book at a rail station, and then I was so astonished because there were so many examples where correlation does not imply causation. However, after doing research in this field for quite some years, now we are very optimistic. Essentially, under some assumptions, in almost all cases, you can really infer information of underlying causality from observational data. So what's causality? We say two variables are associated if and only if they are dependent. It's very simple. And when we say X is causal Y, we mean the effect of interventions. So we cannot define causality just at the statistical level. We have to go to another level. So we define intervention first, and then we can see the consequence of interventions. Intervention is defined this way. Intervention on X, say rain, is defined this way. We can only change this variable directly, but not any other variable, at least for the moment. What does that mean? It means that if I do intervention on rain, I could only directly change rain, but not anything else in the system. So this way, if I later, or at the same time, if I observe another change, I know this change must be the consequence of the variable I intervene on, right? So then this way we can say X is causal Y if there exists different, this intervention on X to set X to different values corresponding to different distribution Y. Since this intervention changed only X directly, now we know, yes, the difference in Y distribution must be caused by the change in X, and hence X is the cause of Y. Of course, you may say this definition is circular. Why? Because if I have no idea about the causality, how can I make sure this is the intervention? Given that the intervention can only change the target variable, but not any other variable directly, right? And at the same time, if you can do intervention, you can define causality, or you can determine causality. However, a circular definition is still useful. Later, you can see by making some proper assumptions, we can just go to this circular world to make sure things are causal. Okay, so this is the outline of this talk. I will just briefly report the recent advances in causal representation learning. I will briefly mention 3 cases, including the case with ID data, independent and identically distributed data, and then I will talk about time series data, and then we can have a look at the scenario with multiple distributions. So in some way, we can say this is a heterogeneous case. And then let's see how we can just make use of the text-image pairs to really understand the concepts, and then do precise generation and refinement for generative AI. So this is a very famous example. Right here, you can see the number of chocolate consumption per capita per year is clearly nicely correlated with the number of Nobel Prize winners, 10 million people, right? And if you take log transformation, you can see the relationship is almost linear and the correlation coefficient is very high, right? Statistically speaking, this is very nice because the correlation is very high, but from our perspective, this may mean nothing. Why? Because without the causal understanding, we don't know what to do. Essentially, we want to understand so many things for the purpose of making changes, right? So if you know that chocolate consumption is a cause, then we can try to say distribute chocolate right every day. But later, actually, in my class, by collecting some other variables, we can infer that no, there are no causal inference in between. Instead, the 2 variables have latent common causes right here. Just from data, you can discover such information. Okay, now how can we solve the problem? We have to discover causality from observational data. So this problem was known as causal discovery traditionally, and recently in machine learning, people have been using causal representation learning. Essentially, they mean the same thing. However, for historical reasons, they may focus on different aspects of the task. So generally speaking, in causal discovery, we try to recover the underlying causal structure from data. And by definition, the causal structure should contain hidden causal variables and relations. However, some time ago, some people believed that we can only make use of the causal relations among the measured variables for the purpose of intervention, right? That's why they mainly focused on the causal relations among the measured variables. In contrast, in causal representation learning, very oftentimes we start with low-level raw data like pixel data, and try to infer high-level latent variables like concepts and relations and so on, right? But basically, both of them try to find the underlying causal representation. So you want to go from the observed variables to the causal representation so that you have a causal explanation, right? And very oftentimes we have latent variables. So the first question in this part is whether this is possible, right? Because a lot of people say, oh, you cannot go from observational data to the underlying causality. That's true in some way. However, with this example, you can see, generally speaking, we always make assumptions. And with assumptions, very oftentimes the problem can be naturally solved. This is a question in the homework assignment for a 4-year-old. Now you can see, basically we can determine the order of the events, right? So which one is the first, which one is the second, and so on. Now you can see, without any difficulty, a lot of people will say, oh, this one should be the first, this one should be the second, third, fourth, and fifth, right? This is the causal or temporal order. This is also causal order, right? So yes, the teacher will say, yes, genius, right? This is right. However, it's also possible to have different solution, different answer. For instance, I may say, oh, this is the first one right here, and this is the second one, third one, fourth one, fifth one. Why? I can say, so at the very beginning, you can see the kid was running. That's why the kid was sweating. And accidentally, the brush has the same color as the painting, and so on, right? You can see a lot of accidental patterns. And then later, the kid started removing the painting from the fence. And finally, after getting done, the kid also washed the brush and everything, right? So now you can see this is also a possibility, although the chance is very, very slim. Why? Because there are so many accidental patterns, right? So this violates the simplicity assumption. So basically, with some kind of simplicity assumption, we can recover temporal order and hence the causal order, right? So basically, this is the idea behind the causal discovery and the causal representation learning. Okay, so how can we solve the problem? Basically, all methods for causal discovery or causal representation learning rely on one property of the causal system. It's known as modularity property. What does that mean? All variables can be dependent. However, from the causal perspective, you can decompose the whole system into a set of separate processes or modules. Those modules do not share any information. They don't share parameters, they don't share anything. For instance, here, rain, wet ground, slippery are dependent. However, we know that the process to generate rain and the process to generate wet ground from rain and the process to generate slippery ground from wet ground are completely irrelevant to each other. They are independent modules in the world. They don't share parameters or anything. You can change one without changing any other. So from this property, modularity property or exogeneity property in economics, or independent causal mechanism formulated in machine learning, then you can derive statistical properties of the variables. For instance, given x, you see z and y should be conditionally independent. Why? Because when I try to determine y, as long as I know the value of x, I don't care about z. It's a different module, right? And this is the conditional independent relationship. And with this, we can develop constraint-based method for causal discovery. Furthermore, now you can see right here, when I consider the process from wet ground to slippery, I have noise. And if x and y, wet ground and slippery, do not share other latent common causes, then this noise term E should be independent from the wet ground. Why? Because E is generated from another module that don't share information. So this is known as independent noise condition. Okay? E and X should be independent as two causes of slippery. Later you can see with this condition, we can even find the causal asymmetry. And of course, if you have non-stationary environments, things can change. However, you can argue that for the right causal model, it enjoys minimal changes, which is to say that only a minimal number of modules should change, and at the same time, if they change at the same time, they change independently because they don't share information. Okay, so basically, all methods can be derived from this perspective. Of course, at the same time, we have to assume some kind of simplicity conditions so that we can find the right model. Now let's look at the setting of the problem. So basically, there are three axes of the problem of causal discovery or causal representation learning, including whether you have ID data or non-ID data, whether you can enjoy parametric constraints for the mechanism or it's parametric, and whether you allow a lot of latent variables. And right here, you can see a summary of the recent results in this field. So we will start with the ID data right here, and then we can consider non-I but ID data, which means we have temporal dependence. And finally, we are going to look at the situation with I but not non-ID data. So in this case, we have independently distributed data, but the distribution is not identical. In other words, we have multiple distributions. Then you can see in each of the cases what we can get. Okay? So roughly speaking, with ID data, the solution is usually pretty weak. Why? Because statistical inference and causal discovery are very different. In statistical inference, we like ID data. But causality basically aims to understand and apply changes. That's why whenever there's a change or temporal information, we can heavily benefit from such information in order to discover causality. So you see, in the latter two cases, usually the results are much stronger, even if the model is non-parametric. Okay, so now let's go. Remember this example. So Marlin Nobeck, with a great last name, Nobeck, collect the data right here with 250 skeleton and 8 variables. Here you can see the data. So this is the ID data. We have a single distribution. Here some variables can be high dimensional. For instance, the cranial shape differentiation is 255 dimensional. And we don't know whether relations are linear or nonlinear. Actually, many of them are nonlinear. So here we don't have parametric constraints. And you may have or you may not have latent variables, but we can do both. So in this case, you can see we don't make use of constraints on the mechanisms, However, we can still make use of conditional independent relations in the data. Here you can see a very quick picture of constraint-based method for causal discovery right here. So the typical method is called the PC algorithm. Peter Clark basically is Peter Clark and my senior colleagues at CMU. So right here, with the PC algorithm, if you assume there are no latent variable or latent compounder in the system, and if you have enough ID data, then it's guaranteed to converge to the truth. Although in many cases, the result may not be so informative. Similarly, even if you have latent variables, FCI is guaranteed to be asymptotically correct. However, because it makes use of only conditional independent relations, very often the result may not be very informative. Whenever it is possible to include a compounder, it will say so. So as a consequence, it could be you may want to make use of other constraints to further refine the result. Let's look at what I mean by that. So here, this is the procedure. We have data on the left, and then from data you can discover independence and conditional independent constraints. And then whenever you see, we start with a complete graph with the PC algorithm. So whenever you see independence or conditional independent, you can remove the link. Okay. So this is because under the condition of causal Markov condition and the faithfulness assumption, we know that two variables are conditionally independent given anything if and only if they are not directly causally related. So 1 and 5, no link. 2 and 4, no link. 2 and 5, no link. 4 and 5, no link. And 1 and 3, no link, right here. And then after this, you can try to determine causal direction. For instance, here, if you look at the relations among x2, x4, and x3, now you can see 2 and 4 are conditionally independent given 1, but not 3. Then this is the only way for them to be related. This is known as V structure, or we say this is an unshielded collider. We say x3 is an unshielded collider because it's a collider right here and it's unshielded. There are no such a thing. So in this case, we can determine V structure, and this is the only possibility. And after that, we can try to determine other direction by doing orientation propagation. So here, if you try to see the relationship between x3 and x5, now you can see that it must go this way. Why? Because if this guy goes this way, then we are going to have a fake V structure because x2 and x5 are causes of x3. Then x2 and x5 should be marginally independent in this case. But in the data, you can see they are independent given x3. So we can avoid fake V structures and so on. And finally, this is the result. Basically, you can see some links are directed and some links are not, right? And at the same time, in PC algorithm, we don't allow latent compounders. So later you can see how we can address those two issues, right? To allow latent compounders and to determine the orientation for all edges. Okay. Now comes the result on the archaeology data. So here we produce a platform called Causal Learn. So it's publicly available and with a lot of methods integrated. So we have the data set as the input, and on the right you can see the output. So geodistance is a cause of climate and the cause of cranial shape differentiation, cranial size, and so on. And also it's a cause of diet, and the diet is finally a cause of cranial shape differentiation. So basically what you eat can change your looks. However, relative to this set of variables, this causal influence from diet to cranial shape differentiation right here is not direct. It takes place via another two variables, including attrition in teeth and some other behavior. Now you can see with a color picture, everything is transparent. For instance, I can still eat what I want to. As long as I can protect my teeth and try to avoid some behavior, then my cranial shape differentiation will not change for that reason, right? So now you can see with a color picture, you can determine not only causal relations, you can also distinguish between direct and indirect causal relations, right? And finally, you have the freedom to make a desired difference. Okay, this is the first example. So in many cases, you want to go further. You want to determine all causal directions. Then if you are willing to make relatively weak assumptions on the mechanism, very oftentimes we can immediately determine causal direction, even if you have only two variables without the time information. So why? This is because of the asymmetry of the two variables under some assumptions on the causal mechanism. So right here, you can see this is a linear non-Gaussian case. We have two variables x, y. We first generate x and then generate y, okay? Where the noise E is independent from x. As you can see from here, this is a non-Gaussian case. Specifically, this is a uniform case. X is uniform and the noise is also uniform. They are independent. Y is a times x plus E right here. And then if you try to regress y on x, you can recover independent residual, right? Because you just recover the true process. But if you regress x on y, in other words, you try to look at the cause x from the perspective of y. You do linear regression, and then on the right, you can see this is a scatter plot of the residual and y, the hypothetical cause. Now you can see they are uncorrelated because whenever you do linear regression, the residual is guaranteed to be uncorrelated from the predictor. However, clearly they are dependent because the distribution of the residual is heavily sensitive to the value of y, right? They are clearly dependent. So generally, you can show that in the linear non-Gaussian case, if you don't have the right causal direction, then you cannot end up with independent residual, as you can see from here. And this is the way to discover the causal asymmetry between two variables. So even if two variable case is a fundamental case, because if you can solve the problem with two variables, then with a lot of variables, you can always try to fix some other variables or condition on some other variables, and this problem will become a two variable problem, right? And you can determine all the direction. The same thing happens to other rather flexible causal models, including the post-nonlinear causal model right here, with the two nonlinear functions. And this nonlinear function F2 can be used to model sensor distortion, measurement distortion, and so on. And additive noise model, which is the special case of the post-nonlinear causal model. Okay, so in reality, very oftentimes the noise term is not additive. That's why the post-nonlinear model actually is very useful, especially in biology and social sciences. Okay, but in all those cases, if you have data generated by such models, you can determine, generally speaking, you can determine which one is the cause and which one is the effect. Now you can see an example. So we are given the values for the two variables x1 and x2 right here, okay? And we have a scatter plot. If you assume x1 causes x2, you fit the model, you estimate the residual and so on, you can see, yes, they are basically independent. But if you consider the reverse direction, assuming x2 is the cause of x1 right here, you fit the model, then you can see you can never find an independent residual, okay? So this means that according to the post-nonlinear model, we'll favor x1 as a cause of x2. In fact, x1 is the altitude of 300 cities, and x2 is the corresponding precipitation. So clearly, x1 should be the cause. So this is a way to discover causal asymmetry, even if you have only two variables. Okay, this is the first case, first issue we want to address. You try to discover the directions for all links. Now let's consider latent variables. You already looked at this example before. In this case, we have 50 questions, and they were designed in order to really discover the underlying personality traits. What can we do? So in this case, again, we have ID data, and very oftentimes, in order to make it simpler, we can assume some parametric models, right? In some cases, we can assume it's a linear model, it's a multinomial, and clearly in this case, in this example, we have to allow a lot of latent variables because we try to uncover the hidden world that generated the answer scores. And the problem can be formulated this way. We have the measured variables, as you can see from here, and the measured variables are related to hidden variables, while hidden variables and measured variables can be related in a very flexible way. Okay, so in the general case, we allow the relations among latent variables. We allow causal influence from latent variable to the measured variables, and also relation from measured variable to the latent variable. It could be very flexible, but you can solve the problem. Specifically, here, let's look at linear case. We have some results in the nonlinear case, but at this moment, it's too complicated. Probably in one or 2 years, the results can be refined. So right here, in the linear case, first of all, this is the result by making use of the rank deficiency condition given in this paper right here. So now you can see, yes, we have all those questions, O, E questions, A questions, N questions, and C questions, right? And first of all, the results seem to be somehow consistent with the big 5 personality traits, right? You can see different kinds of questions are basically clustered right here. They are clustered, and you can see more information. For instance, some questions are actually related to multiple dimensions, like O9. I spend time reflecting on things, right? It's related to not only openness, but also neuroticism, okay? And the second of all, you can see a lot of new information. Let's consider one example. In this corner, you can see from the openness questions, actually we can discover 3 latent variables, L1, L6, and L4. And if you look at the questions adjacent to those latent variables, you can see their meanings. L1 basically is about imagination, and right here, L6 is about understanding, and L4 is about creativity, right? And furthermore, you know that imagination and understanding are causes of creativity. It's sensible. And from this, we can even try to come up with new ways to do intervention. For instance, suppose I'm very good at understanding things, right? I read Wikipedia all the time. And at the same time, my imagination is not very good, and my creativity is not kind of impressive. What can we do? Maybe I should try to find a way to practice my imagination skills, right? Probably I should get away from internet and try to imagine something and try to see the consequence and so on. And this might be a way to finally improve my creativity. Okay, so once we have a very clear causal picture, we can try to find the intervention we can apply at the least price. Okay, this is the second example. Good. Now let's look at the temporal case. So we have time series, and then we can try to discover causality. A traditional way to discover causality from time series is to make use of Granier causality, right? Granier himself said Granier causality is not necessarily true causality. However, under some relatively strong assumptions, Granier causality is true causality. But here, we would like to go further. We don't try to discover causality among the measured variables, because very oftentimes causality happens in the hidden space and the relations between the hidden space and the observed variables. Let me just give one example. So suppose now we have video data and you try to see what's going on, or try to understand the video data. What can we do? So in this case, you can see we can just model video data as high dimensional time series. And then the high dimensional time series is just an unknown flexible function of the underlying latent processes. It's a vector, right? Vector of latent processes like objects and so on. And the objects latent processes can be related. There's only one assumption in this problem. So if you have the right latent representation or the right way to look at the world, then it takes time for causal influence to take place, meaning that the latent processes are not instantaneously related. Given the history, they are conditionally independent because there are no instantaneous relationship. That's the only essential assumption. Then given that assumption, even if everything non-parametric, generally speaking, we can recover the latent processes up to the component-wise transformation. So basically, the world is transparent because you can recover each of the latent variables, like kind of balls and so on. Let me just give one example. So this dataset is known as a mass spring dataset. Here you can see there are 5 balls moving around with different colors. Between some balls, there's a hidden spring. And from this video data as input, the system directly outputs 10 hidden variables or processes. They just correspond to the x and y coordinates of the 5 balls. At the same time, the relations can be discovered. So now you can see everything is transparent. Just from the pixel level video data, you can immediately find a representation corresponding to the underlying meaningful objects and the relations right here, and so on. So now we are trying to develop a foundation model for video understanding so that you don't have to store pixel level video data, right? And you can directly just produce the high-level concepts and relations, and later the analysis will be based on the learned representation. Okay, now let's look at multi-distribution situation very quickly. So right here we have independent but non-identically distributed data. In this case, very often we don't have to make use of parametric constraints, but still we can discover something very meaningful. First of all, you can see basically Semmelweis made use of this setting. The two clinics used almost the same techniques, but very different mortality rates, right? You can see the difference, the distribution was different. And then he tried to see the essential difference. And finally, he came up with a hypothesis. This is exactly what we try to do. Now let's look at example. So right here, suppose we have two data sets. Right here, this is the first one, and this is the second one, right? Or we have two domains. And suppose now we have no alignment information. We don't know the pairing information. We don't know they correspond to the same meaning. Right here, we have no idea. We just see different pictures, right? Handwritten digits. So you try to see the pairing information, and furthermore, you may want to see what's the difference between the two domains, the essential difference. Now, from your perspective, what's the difference? Right? You may say, oh, it's basically the rotation, right? The angle is different. That's great. But mathematically speaking, I can say originally this one will correspond to rotated 6, and 6 will correspond to rotated 0, and so on. This is still a valid mapping. Why? Because in this case, we are giving the marginal distributions or data corresponding to the marginal distribution, and we try to see the alignment of pairing information given by the joint distribution. We know that going from the marginal distribution to the joint distribution is so difficult. It's an irreposed problem. Without proper assumptions, we cannot solve the problem. Now you can see with some assumptions, plausible assumptions, we can immediately solve the problem. What's the assumption? In order to motivate that, let's look at a more complicated problem. So right here, we have summer images and winter images. Usually we don't have the data, right? Usually we don't stay in the same place, right, for half a year. So now you just have the two sets of images. How can you see the difference? How can you see what you mean by season? And how can you really go from one picture, say arbitrary summer image, to the counterpart in the winter? It's very difficult, right? So in order to do so, we have a generative process. Basically, images have two parts, content and style. The content basically is the information that does not change across data sets. And the style is the minimal information that can be used to explain the difference across domains. That's it. Now you can say by definition, style should be as minimal as possible. And then technically, we just make use of one assumption. We try to minimize the influence of style on image during generation or translation. How? And we can just use a minimal number of changing components or minimal number of components for style or representation. That's it. With this single condition, we can solve so many problems. Let me give one example. So this is the image generation problem. So here we are given two separate domains without the pairing information, right? And then we were asked to generate two pictures across the domains corresponding to the same content right here. So here we are given two sets of images corresponding to the female, male, and then let's just generate two pictures with the same identity or person but different genders. What can we do? In this case, we just try to identify the style variable, and we try to identify the generative process. Fortunately, under some assumptions, the generative process is identifiable under the minimal changing principle, which was just formulated. Okay, and then we can just go from the marginal distributions to the joint, and then we can just go from one data point in one domain to another domain, or we can just do data generation with multiple domains. So here at the bottom, you can see the result. On the very left, you can see the result produced by our method. Basically, you can see it's almost the same person, right? But clearly gender is different. Almost the same thing. With other SOTA methods, mainly developed by computer vision researchers, you can see very often there are some extra distortions, as you can see from here, the winkle, and here the sunglasses, right? So principles are very important, and very often times we automatically formulate and make use of those principles when we try to understand new scenarios. The issue is how we can formulate those principles so that machines can do something smartly and more powerfully. Okay, now let's look at the last part. I think the last part will maybe 8 minutes, 7 minutes will be good enough. So let's try to understand the concepts so that we can do image generation and image refinement and editing. So we know generative AI is very powerful. So with text to image models, we can just generate some pictures, nice pictures from the prompt, right? However, one thing is almost completely missing. Of course, recently, some products were just released, but basically they made use of paired data. What can we do? So basically this example. Here, first, we can ask, say, DALL-E 3 to produce a picture of a happy girl in the garden. This is very nice. Now, if you say, oh, could you make the girl angry? Now you can see, yes, the girl is angry, but the background is different, right? And everything can be very different. This is not controllable, but as a smart artist, you want to generate a very nice painting this way. You first draw a painting and then you focus on the details you want to modify, and you can just make refinement, right? And this is our goal. We try to make sure machines can really understand concepts and relations so that it can just modify exactly what you want. So now you can see more examples. For the same reason, it's very hard for generative AI to do extrapolation. So here in this example, you can see first we generate a female face. It's very nice. Now, can you add mustache? Nothing happens. Okay. And this example, you can see you saw this example before. We want to change the facial expression, but yes, the background become very different. Okay. Later, you can see how we can deal with this problem. We start with a causal process we assumed for this problem. So with the causal process, then we can try to establish guarantees. We know, yes, all those concepts are identifiable, and then we can allow machines to directly understand the concept and relations. So this is assume the causal process to relate text and images. From text, right, we try to define meanings, and we have the atomic textual concepts and relations, right? And from images, we also have the visual concepts, the eye right here. This is text concepts. So, and clearly they are related. And furthermore, we know that generally speaking, textual concepts right here would be more informative. When we say blue, basically in text, blue is just a binary variable, right? Regarding whether it's blue or not. But in the images, there are so many different levels of blue, right? So in other words, the atomic concepts derived from images would be more informative, and they are basically generated from the concepts, from the textual concepts, but with actual information. Right here, you can see it. At the same time, the relationships among the two different worlds should be as simple as possible, right? So the connections right here, the links to link textual concepts and visual concepts would be as sparse as possible to avoid the kind of actual complication. Interestingly, now you can see by making use of only two assumptions, all those concepts are identifiable from the text image pairs. So the first assumption is the sparsity constraints on the cross links right here. They should be related in a very sparse way. And second of all, we have a conditional independence in the image concepts given textual concepts. Why? Because textual concepts should provide major information to explain the difference or the dependence in the visual concepts, although each of the visual concepts can be more informative, right? By more informative, I mean each of them can also contain the influence from some other even continuous variables, right? To describe, say, the level of blueness. Okay, now you can see on the left, you already saw this result produced by OpenAI. Now you can see the result produced by our platform. So first you generate a female image, and then you can see now, yes, although it's weird, the result is kind of natural. You just add a mustache. And this is because extrapolation is also related to the ability to go to concepts and make use of proper sparsity constraints. And on the right, you can see now you can generate a picture of a smiling girl in garden, and then you can just make the girl surprised without changing anything in the background or any other feature in the image. So it's completely controllable, just because machines can learn to focus on exactly what you want. And right here, you can see more results for image generation and refinement. So you already saw the first ones. And in this one, it's an elderly man with a cat. You can see we can just change the color of the shirt without changing anything else. Okay, but with other tools, including DALL-E 3, Sana, and so on, you can see some extra changes. Okay, and finally, we can just let peacock eat ice cream. So with this prompt, you can produce this picture, and then with one more prompt, a peacock eating white ice cream, you can do modification or refinement. Now you can see the only difference is to make the ice cream whiter, right? So machines can draw this picture to describe a novel scenario. At the same time, the machine can really make the change you want to enforce. Okay, so to summarize, first of all, learning causality from data, even purely observational data, is not really mysterious. Under some assumptions, we can do so. Of course, without assumption, with any assumption, we cannot go further. But fortunately, a lot of assumptions are plausible, and some assumptions, the majority of the assumptions are testable. So from data, you can try to see whether those assumptions are plausible, and if they're not, you may want to make use of another set of assumptions and corresponding methods. And second of all, you can see generative AI can clearly benefit from causal modeling. First of all, I didn't describe this part, but basically with causal modeling, you can really do counterfactual changes, right? To just make minimal change to achieve your goal. And second of all, you can see minimal change is a very important principle in order to do translation, generation, refinement, and so on. And furthermore, you can really allow machines to go to the level of concepts and relations so that the machines can generate nice pictures or nice text in new scenarios, right? It's a way to achieve extrapolation, and also it's a way to achieve kind of arbitrary changes. And finally, in the previous result, you can see DALL-E 3 made use of 600 million data pairs, while we only made use of 1.5 million data pairs. So causal principles basically provide additional constraints. As a consequence, the model or the training process would be more energy efficient thanks to the constraints or principles. And finally, we just try to make causality, causal method or causality methods transparent so that we can really make causal process behind what we see transparent in the world. Okay, thank you very much for your attention.
Thank you, Dr. Zhang, for the very informative talk. And I'll open the floor for questions now.
Thank you, everyone. Any questions?
Yeah, could you go back to the slide which right how we went from a text D to an image I with the steps in the middle?
Is it audible, Dr. Zhang?
Oh, can you repeat the question, please? It's not so clear.
Okay. So basically, could you go back for a second to the slide in which you had a text D that eventually morphed into an image I, and it had all the graphs in the middle representing the individual features of the text and then interconnected images?
You mean right here? You mean they assume the generative process to relate images and text? Is that what you mean?
That's the one, yeah. I just wanted to know what exactly is atomic visual concepts here? What does it represent? Is it related to in an image, say, already generated, each of the human identifiable objects within it, or is it something like pixels or something like something?
Wonderful. So it's not really pixel level concept. So right here, we did a lot of studies and seemed for instance the shape, different shape, color, and so on would be atomic concepts right here. So this is because if you have the generative process images right here, you don't have, if you specify the pixel level concept, then it's almost impossible to draw the connection between text and those concepts, those pixel level concepts. So I don't think, oh, okay, those results were not given. So for instance, here you can see, we can learn the concept of shape. You can just try to change some of the learned atomic concepts. You can see the consequence. We did a lot of studies. Shape can be learned. For instance, here you can see we can change Hulk to Batman, the shape, and other shapes and so on. So basically, the color, shape, and textual information, and so on. All those concepts can be learned. Of course, right? It may not be completely aligned with what we understand from images. And the dimensionality could be much higher. Here we use 1024 dimensions for the concepts. Is that answer? Could you go ahead?
The question here is the shape of which object is.
Yes, right here you can see. Yes, in this case you can see we can learn the shape of Batman.
But it's not in the
So
text.
and this one may not be the atomic one. However, it's a way to combine different atomic concepts to produce these new concepts. Because if you put atomic concepts together, you have new concepts, combined concepts.
So the text is just Hulk. Batman is not in the first. So in the first image, what does it learn? Hulk?
Oh, this is generated result. So basically, you can see this picture. Then basically, the machine can learn what you mean by hook, and what you mean by horse and riding and so on. And then we just do editing or refinement. We just change hook to Batman shape. Now you can see whenever you want, you only want to make that change, right? So if you use this prompt or use an instruction saying making the hook just give the hook the Batman shape, then you can see the picture produced in the middle right here. So this means the machine can really learn what you mean by shape and what you mean by Batman shape, and then just change the shape of the hook to the Batman shape.
Kept the color of the house.
So does it mean that there's to keep a relationship between the concept and the region of the image?
Yes. Yes, and we assume the relation among concepts basically are fixed. You just have different kind of concept activated.
So, sorry, basically you have like a training data set of minimal pairs in images?
Oh, training data is, can you say the last part again?
So does that mean that you have the training data of minimum pairs?
Yes,
No.
like.
Oh, by minimal, what do you mean by training data minimal pairs?
The minimal changes.
Yes.
So like changing.
Oh, no.
Batman.
Yes. Now I see the question. So basically, they are just arbitrary pairs. So in the pairs right here, you can have complex changes, right? And very often times, yes, the changes could be very complex, right? You just try to cover many scenarios. The essential part is that by making use of some principles, as you can see from here, you can allow machine to just learn the basic concepts. And the basic concepts are not specified directly. You don't, like in machine learning, in computer vision, a lot of people are trying to do editing by making use of paired data. Here, we don't use paired. By making use of paired data, I mean the following thing. I have two, right here, I have the first picture, and then in the training process, I will present a picture with, say, additional mustache. I say, oh, this is basically how you can edit the image to add mustache, right? Here you can do it with paired data. It's kind of supervised, but in our case, it's completely unsupervised. We just try to make use of the arbitrary text image pairs to understand the concepts, and then if you can discover the concepts and how the concepts can generate images, then you can just change suitable concepts, right, to make a difference, while you can just maintain the remaining concepts. So this is what we mean by minimum change. You just change exactly what you have to.
Okay, I see. Thank you very much.
Thank you.
Maybe we can take one last question if somebody has any, or you're welcome to reach out to Dr. Zhang offline if you have a question.
So just for curiosity, so going from zeta t to zeta I, when you say is unsupervised, what exactly it means? Because zeta t, I understood that is your starting point, and how you can go to zeta y that you transform Hulk in Batman.
Yes. So right here, now you can, when I say this unsupervised, I mean relative to the task of image editing is unsupervised because we don't have the paired data for editing, right? Alternatively, you can just have paired data, right? I can give you this picture and then give another picture with mustache. I have a label. This is supervised. In our case, we just have a bunch of paired data, right? A lot of just arbitrarily collected paired data. And just from such data, we just try to recover all those relations and concepts. Is that the answer to your question? I mean, we try to learn the concepts and align them from paired data, right? The setting is very different from, you can think of this as a pre-training process. Just from arbitrary pairs, you want to learn the inner representation with the concepts and the relations. And then later you can make use of the learned representation for a number of different tasks. One of them is to do image refinement and editing. And we are doing something similar in text generation. Is that answer to your question?
To some extent.
Or maybe you can add a few words to describe the gap.
Where I am confused is when you first say it's not supervised, but then you introduce the concept of pairs. So pairs brings me that is supervised. So where I am wrong understanding.
I see. So I have 2 points to make here. First of all, the concepts from text are also learned. We don't directly specify textual concepts. What we are given is just arbitrary prompt and image pairs or text image pairs. We just collect a lot of images with captions. That's it. We just have data pairs. And right here, if you just try to say predict the caption from the tag from the images, then we can say, oh, right here is a supervised, right? Because you try to predict this guy, one target variable from some other features. This is a supervised learning problem. But our task is different. We just make use of those features, text features and image features, to learn some inner representation. And relative to the task of image generation and editing is unsupervised, because for editing, if you want to go with the supervised learning setting, you have to present paired data this way, right? Before and after editing, you have 2 images, right? And then you can just try to learn the difference. In this example, you can try to learn the difference in the image corresponding to adding mustache. And this is the supervised learning manner for image editing. We are not doing that. We just try to make use of pairs to learn the inner representation, and then we directly make use of this inner representation and the prompt to generate new images or to refine images. So when I say it's unsupervised learning for image editing, I mean, we are not using paired data for editing, but we make use of text and image pairs in order to derive the inner representation. Are we on the same page?
Thanks, Dr. Zhang, that answered the question. So we'll have to move forward. There are a couple of questions I still believe in the audience, but maybe they'll take it on off